This is Tuesday, October 29th, year of our Lord 2019. Hello?
Johnny.
Hey, Joel.
Johnny. Hello?
Julia. Johnny.
Hello? Johnny.
Hi, Johnny.
Julia.
Julia.
All right, here we go, chapter 4. Chapter 4 is getting us to start working with fractions. When you hear the term rational numbers, you're fractions. A rational number is any number that can be written as a fraction. So, when it comes to number sense, the first numbers you learn, the counting numbers, are whole numbers, if you include 0. All the numbers you've learned are called, get this, real numbers.
Really?
It always fascinated me when the teacher would talk about real numbers, because the first thing that would come to my mind, like some of you, is, there's numbers that aren't real? And then you learn when you get into high school and advanced math that there are these things called imaginary numbers.
Wow.
So you're learning about rational numbers that are all the whole numbers that you learned when you were really small, the ones you can count, right? But then it's all the numbers in between those, like 1 and 1/8, 1 and 2/8, 1 and 100. Any number that can be written as a fraction. So since we're going to be working with fractions, we got to go back and learn how to, or remember how to reduce fractions, write them in simplest form, lowest terms, reduced. We got to learn how to make common denominators, because you can't add or subtract fractions unless you have a common denominator. So we got to go back to learning GCF and LCM or LCD, because your lowest common multiple becomes your lowest common denominator. We got to learn greatest common factor to reduce, right? Now the only difference is, instead of just working with like 4/8 gets reduced to 1/2, or 2/3 you can make 6/9. There's going to be algebraic expressions in your numerator and denominator. So instead of just being like 4/10 and reducing it to 2/5, it might be 4x over 10x squared or something like that. But still going to be the same rules. And we started you with finding factors by breaking down a number into its prime factors. And you only had, what numbers yesterday? 1 to 9. Ready? The first one, only the positive factors of a blank number are the number and 1. What kind of number has, for its factors, itself and 1, Rachel?
Composite.
No, opposite. Composite is numbers, where you can make up that number by all kinds of. What's the opposite, Rachel? Prime. Prime itself and 1. Number 2, you were supposed to write all the factors of 18. Hopefully you wrote 1, 2, 3, 6, 9, 18. Say amen.
Amen.
Then you wrote all the factors of 27. 1, 3, 9, 27. Then you wrote all the factors of 41. 1, 41. Rachel, that makes the number 41 prime, because it's only factors where itself and 1. Number 5, 66, a little tougher, because this one isn't in times tables. You got 1. You got 2, because 66 is even. Even if you didn't know how many times 2 went into 66, you thought 2's got to go into 66, it's even. Then you figured out it was 33, right? So you got 1, 2. You didn't know how many times 3 went into 66 at first, but hopefully Jordan remembered. Let's see, 66. 6 plus 6 is 12. 3 goes into 12, so 3 goes into it. I got to figure out how many times. And you figured out 22. And then you went to 4, and you said no. 5, no. 6, times tables. 6 times.
11.
So your factors are 1, 2, 3, 6, 11, 22, 33, and 66. Number 6, okay, gets a little tougher. The prime factorization of 28. Now, how many learned a different way other than the tree?
Oh,
How many learned this?
yes, the box. Didn't you? Oh, yeah, did it
You with me?
Yeah.
What makes 28? 7 times 4. What makes 4? 2 times 2. What are we left with on the outside? 2 2s times 7. You can do it, listen, if you've learned it that way before and that's more comfortable, either way, you're going to get the same answer. You're going to be left at the bottom of the tree with 2 2s, 2 squared, and a 7. Whatever fits your mind, whatever one you think is easier to work with, the box or the tree. Yeah.
If they, like from the box, if they answer, but if it's 10, or if it's a number where it's built, like the second, like that 7, but they was even, then what would you do with it?
What? Oh, like, so I didn't start with a prime number out here.
Yeah.
Yeah, you would, you have to start with the prime number out there, I guess.
Okay. You got it, what do you want?
See, I don't work with this very often. I like this.
Yeah.
But, good question, though. Yes? When you end up with 2, 2, and 7, they want you to always say it as a power of 2. Got that? So that's what it should look like. 2 squared times 7. Number 7. Prime factors of 55. This one should have been easy. 5 times 11. Number 8. Prime factors of 82. Remember, 1's always a factor. You eliminate that. 1 and 81 are factors. If there's no other factors, it's prime. It's just 1 and 81. But your next number after 1 is 2. So you've got a clue that 82 is not prime because 2 is going to go into it because it's even. So you had to think, what times 2 gives you 81 or 82? And the answer is, and then to be sure, you think 3, no, 8 plus 2 is 10. 4, no, 4 times 20 is 80. So it must be 80 and then 84. 5, no. 6, if 3 doesn't go into it, then 6 can't. There is no rule for 7 and 8, but your times tables tell you 7 times 12 is 84, so no. 8 times 10 is 80, so no. 9 times 9 is 81, so no. Got it? So you figured out that it was just 2 and 41. Yes?
I got the wrong one.
Lisa's
Oh, goodness, my
For once, what they do it.
2 and 41. And number 9, 96. Does it matter which 2 factors you pick at the beginning? No. Some of you might have thought, I'm going to pick the largest ones I can think of from my times tables. 8 times.
No, 12.
Who picked 8 and 12 first? Nobody?
I did.
Okay? Because you know your times tables so well, middle schoolers, that when you see 96, it's almost automatic. It comes up in your brain, 8 times 12. You practice those so much in your elementary days that comes natural. You could have used 48 and 2, right? And had 2 just hanging there and done 48 all the way down. I'm going to do 8 times 12 because that's my times tables. 4 times 2, 2 times 2, 2 times 6, 2 times 3. Either, any way you do it, look at the bottom here. 1, 2, 3, 4, 5,
2 to the power
2 to the 5th times 3 will give you 96.
I thought 2 to the 4th times 6. 10.
Because you left this, so you didn't do this. If you got 2 to the 4th times 6, you got 2 to the 4th times 6. 6 isn't prime here, so you got to keep going. All right, number 10. Let's do this together. Ready? You're making a quilt out of 120 square patches. What are the 2 most reasonable rectangular arrangements for the quilt? there's 120 patches. Let's start with this. What would be a reasonable quilt? 2 rows of 60?
Yes.
No.
No!
Yeah.
Imagine you've got a quilt. What's a quilt do? It keeps you warm, right? You're snuggling up by the fire. It's winter time. You're on the sofa, the couch, whatever, and you got your quilt with you, and it's 2 by 60. Good luck covering up with that.
Yeah, you just wrap.
So
you
that's
have
what
to
they.
hold it and then you go in a circle and it wraps around you. Oh yeah.
Good luck with that.
Nobody.
So when they say what are the 2 most reasonable patterns, that's what they mean. You're not going to make a quilt squares in a line unless you're Noel and you're playing a cocoon. All right? So what's a reasonable pattern for a quilt? A quilt you want to be long enough and wide enough to cover you, right? So this is what they say. They say to list all the factors of 120 as step 1. Then in step 2, take all of those factors of 120 and just pick out the ones that make 120. What do they mean by that? For instance, 2 times 60. Is 3 a factor of 120? Yes, but 3 times 60 doesn't go together. That makes 180. You understand what they're saying in number 2? Take all of your factors of 120 that actually make 120 when you put them together. So I just gave you one. Our problem-solving strategy, whoops, on camera, I gotta stay here. One of them would be 2 times 60. We already decided that's not reasonable. 3 times 40. Is that any better, Bella? To have a quilt that's only 3 wide and 40 long?
Yes,
No.
that might be a little bit
Noel's
better.
chrysalis notwithstanding, that's probably not the best option. 4 goes into 120, 4 times 30. Not much better. Only 4 wide, 30 long. What would be the best possible pattern to make that quilt if you had 120 patches? What do you think?
12 times 10?
12 times 10. What would that look like? 12 by 10. Yeah. Right?
Tall. Like, taller.
It's a little,
You can turn it.
whatever, you can turn it. It's a little longer than it is wider. Is there another one that would be reasonable? Besides a 12 by 10. They've got 2 listed here. They got a 12 by 10 and what other one might be reasonable? Think. 11 times 11 does not make 120.
14 times 8.
14 times 8 does not make 120. 225.
I'm trying to think of.
15 times 8 is the other one they have. 15 times 8 is pushing it. That's
Yeah.
What about 5 times 24?
no, Noel.
5 rows
No,
like
no,
this,
no.
and there's 24 down.
No.
Or 24 across.
All right, moving on. Our job, not our homework, our job now is to work through 11 through 49. I'm sorry, 11 through 34. I was looking at 49 in number 34. 11 through 34, go. And I'm here. 11 through 34, and it's a right now job, not a homework job. We're on 171, I believe. 11 through 34. Anybody done with number 12 yet? And I'm not joking, because if you got right to work, boom, done with 1, 2, 17, and 34. And now you're writing factors of 64. Remember this strategy. Number 11. I would go like this. 1, 34. 2, 17. 3 doesn't fit. 4 doesn't fit. 5 doesn't. I'm done. Number 12. What's the number? 64?
Yeah.
I think there's going to be a lot, so I'm going to spread it out a little bit. 1, 64. Does 2 go into 64?
Yeah.
Yep, it's even. How many times 2 go into 64?
32.
Does 3 go into 64?
No.
6 plus 4 is 10. No. Does 4 go into 64? That's a tough one. It's not my times tables. Let me think. 4 into 64.
Yeah, 16.
Oh, yeah.
16.
5 doesn't, 6 doesn't, 7 doesn't, times tables. 8 does. 9 doesn't, 10 doesn't, 11 doesn't, 12 doesn't, 13. Done. 8 times 8.
Oh.
Hmm.
108. It's going to take me all the way across the page. 108 is a big number and it's even, so I'm going to give myself a lot of room. All the way to the other end of the page. Does 2 go into 108?
Yeah.
It's even. How many times? Think.
54.
108. 1 plus 0 plus 8 equals? 3 goes into 9, so 3 is going to go into the whole thing. Also, because 3 goes into it and it's an even number, 6 is going to go into it. And think, 4 goes into 100. 4 goes into all the hundreds, right? 4 quarters make $1. 8 quarters make $2. 4 goes into all the hundreds. So 4 goes into 100, and you got 8 more. 4 is going to go into it. The hardest one's going to be this. Oh, we already said 6 goes into it.
So does 9. Because
So you
12
got
times 9 is 108.
3 times, did you figure out 3 times what gives you 108?
27.
20, no, 34?
36.
Oh, 3. I didn't know that.
Listen, here's how you do that mentally. You think 3 times 30, 90. 3 times 6 is 18. 90 and 18 is 108. Practice, practice, practice. We already said 4 goes into it. If 4 goes into 100, 25 times, because 4 quarters make $1, 2 more 4s, 27.
And then 6 and 8.
We decided 5 doesn't. We decided 6 does since it's even, and 3 goes into it. 18. 6 times 10 is 60. 6 times 8 is 48. 60 and 48, 108.
9 goes in. Yeah, so it's 9.
What do we get here?
9 times
18, 9. Wow.
9.
I thought I spread it out enough. 1, 2, 3, 4, 6, 9, 12, 18, 27, 36, 54, 108.
Now we have 175.
That's a lot.
It's all on.
175 is not going to be that many.
1 in 75.
Yeah, 175. 25.
175 is not going to be that many. First of all, you know it's not even, so 2's out.
4.
And if 2's out, and 4's out.
So does 5.
Oh, I forgot to drop.
1 and 175. 5.
7.
8.
Just 7 times.
Well, 7 will too, yes, but 5 goes into 175 how many times?
5.
5 goes into 175 how many times?
35.
35. 150 plus 25 gives you 175. Did you do that mentally? 5 times 30 is?
Go ahead.
5 times 3.
I'm done. 15.
So 5 times 30.
She said that I was down.
Come on.
What?
Peanut. 5 times 3.
15. Oh, 115.
So 5 times 30 is 150. How much more do you need? 25. That's 5 more 5s. 35. Work on that. Don't give up. You're only 12? How old are you?
$15.
So because you can't do it
I'm
yet,
focused with sports. That's 15.
because you can't do it yet at 12, Dina, does that mean you'll never be able to?
Yes.
No. Yes, Cam. 5 times 35 is 175.
Yes. And then 5 times 25.
7 times 25. 157, 25, 35, 175.
Factorization.
And then you get a break, 15 through 18. You just got to write one word. Prime or composite. 21's odd, so it makes you think for 1 second that it might be prime, but no. Because in your times tables, you know 3 times 7 is 21, so it's composite.
So
34.
34.
You know what? Instead of copying that whole factor tree on 23, 24, and 25, you're going to do through 22 and then jump down to 26.
Yeah.
So you're not going to do 22 through, or 23 through 25. Hey! Whoa! How are you? How you doing? Good. Wait, where's your official Heartland visitor? Oh, wow.
I honestly didn't. No idea.
Hi, Johnny. Hi, Johnny.
Wow. Hey, Johnny. All you're good at is making layups. How are you? You can't honestly shoot threes because you passed me. If your parents, Julia, Bella says hi. If your parents are right there, no offense. Johnny's a good basketball player. He can just back me. It's okay.
Here's Micah's shoe.
Julia, we'll see you tomorrow. I forgot my phone. Wait, you will? Bro, Johnny, can you
Mike, you gotta jump up.
Nothing happened. Also,
Okay, everybody, whoa. Everybody understands you are not doing 23, 24, 25, right?
Yes.
Is right? You should all be done with at least 18.
I am on 19 because I don't want to do
27.
I'm going to start doing, I'm going to do 19 and 22 on the board. Well, then I'll affirm that you know what you're doing. 56. I know from my math facts that 7 times 8 gives me 56. And 2 times 4 gives me 8.
Oh, wait, seriously?
So, what is 56 prime factor? 2 to the power of 3 times 7. That was number 19. Number 22. The number is 135. 135 is not part of my times tables. However, I know that all numbers that end in 5 or 0 are divisible by 5. And what I like about that is 5's prime, so I'm done with that side. I got to think, what makes 135? 5 times 5 times 27. What makes 27? 3 times 9. What makes 9?
3 times 3.
So you're, too many people doing their own thing. Your answer to 22 is 3 cubed times 5. 19 and 22 are on the board, so you can look at it and say, yeah, that's what I got. 2 cubed times 7.
We don't do 23 cubed, 25.
And 3 cubed times 5. 26. 26 asks you this. Explain how you can create 2 different factor trees for 540. Do they both result in the same prime factorization? Yes. We could have started this with 2 times 28 if we wanted. or 4 times 14. You're still, when you get to the bottom, are going to get the same prime factors. Everybody got that? 27. Toughest one so far, because it's not just a number, it's got variables attached to it. But Elise says, that's okay. She likes monomials. So 15CD, if I was going to factor that out, this is number 27. I'm going to factor the 15 and just make it times C times D. You can't make the C and D any smaller. Do you understand? It's just one C and one D. So I would factor this out. 3 times 5 times C times D. That's your answer to number 27. You can't make the C or the D any smaller. It's just one C or one D. So that's prime. 3 times 5 times C times D. This is number 27. I'm going to do 29 on the board now. Because 29's got letters that I can make smaller. One of these days, I'm going to be able to write on the board and everything's going to be in order instead of all over the place. Probably not going to happen, but here's 29.
Just make sections.
29 is, because I never know which one I'm going to have to do. 9a squared b to the fourth. Is that what it says?
You just do a ball.
Okay. Work with the number first. What's 9? Prime factor. 3 and 3. So 3 squared. Everybody with me so far?
Yeah.
If I did the tree for 9, it'd be 3 times 3. So I don't write 3 times 3, I write 3 squared. What makes a squared? Toughest question yet. What makes, if I was going to factor out a squared and break it down to its smallest parts, so you know what, since they're doing that, I'm going to write 3 times 3. Since they're undoing the squares here, they're undoing the powers now. So I'm going to write 3 times 3 times A times A times B times B times B times B. Now that looks silly, but that's what they want you to do on 29. To break it down into its smallest parts. Then, if you were giving your final answer, you would put them all together. 3 squared times A squared times B to the fourth. But on this in 29, they want you to factor it out. What are the factors of A squared? A and A. You understand that? What makes A squared? A times A. Got it? Got it? So you do the same thing with 30. So it would be n times n times n times m times m times m. After you factored out 48 into 2 times 3.
I like these problems.
No, 2 times 2 times 2 times 2 times 3. 48 should look like this. 2 times 2 times 2 times 2 times 3.
Times n times n times n.
Times m times m times m. Yes. All right, we down to 31. Old Glory. Always good to bring Old Glory into math class. If you've ever looked at Old Glory for more than a few seconds saying a pledge and you're not really looking at it, you'll notice that the design of the stars, they're not nice, neat. It's not a nice, neat box or a rectangle, is it? You've got the top line, and then the next line's kind of in between the stars of the next one, right? Well, has there always been 50 stars on the flag?
No.
No. There's only 50 stars since 1960, when Alaska and Hawaii became the 49th and 50th states. So before that, there was 48. Before that, there was 40, and so on. It started with how many? 13, good. All right, so the question is, some U.S. flags had a number of stars that could have been arranged in a nice, even columns and rows. How many stars would have been on the flag where you could have made even rows and even columns, where it would look like a nice rectangle, evenly distributed? One on top of the other, one straight across and straight down. How many states would there have been to be able to make the flag like that? I'm sorry, they tell you. When there was 15 states, how could they make their stars even? Yeah. 3 by 5. When there was 28 states, how could they have made their stars even? Jordan, 28 states. They could have done 2 by 14, but what would be more reasonable? Rachel, 4 by 7. Oh.
That was weird.
Yeah. Okay. What's next? 30. When there was 30 states, what would the nice, neat rows and columns look like? Cameron. 6 by 5. And when there was 49 states for a very brief period of time. Very brief period of time, there were 49 states. Hawaii came shortly after Alaska. How many, what would your flag look like? 7 by 7 square. Perfect square. Turn the page. Okay, listen, question is, why didn't they do 5 rows of 10? Because the design of the flag gives you that corner there, right? 5 row, 10 long, 5. Just remember. All right. Why'd we do all that? Why'd we do all this factoring? So we could find the greatest common factor. Why do we find the greatest common factor? Hey, whenever you get a chance to wave Old Glory, take it. Why do we find the greatest common factor? So that we can reduce fractions, to put them in their simplest form. So let's look at page 173, middle of the page. A common factor is a whole number that is a factor of 2 or more non-zero whole numbers. That sounds fancy for, if I got a number that goes into 2 products, it's common. Give me a common factor for 12 and 16. 2. 3 doesn't go into 16. So for 12 and 16, it would be 2 and 4, right? What's the greatest of those? 4. So that's what we're going to be trying to do, to find common factors and then the greatest common factor. Except this time, there's going to be letters involved.
No.
By the way, if I come across a fraction that looks like this, are both of those numbers prime?
No.
No. But they are prime to each other. In other words, only one of these numbers is prime, but when you look at the 2 numbers together, they don't share a common factor. So they are called, ready? When it comes to how they're related to each other, they're relatively prime. They are prime to each other is another way of saying it. 9 and 17. One of them's prime, but the other one isn't. But they are prime to each other. They don't share any other factors except one. Are you with me on that, Dominic? Both numbers don't have to be prime to be relatively prime. Relatively prime means they're prime to each other. Make sense? You sure? How about this one? Relatively prime.
Yeah. No.
Yeah. Yes.
No.
Yeah, because they're, listen, if they happen to both be prime, well then, guaranteed they're relatively prime. Because if they're both prime, they're only going to share one as their common factor. I'm on the middle of page 174, because I just talked about the top, page 174. Number one, middle of 174. Find the greatest common factor between 12 and 18. What's the largest number that will go into both 12 and 18? If you can do it mentally, let's do it. I'm hoping that everybody in the room could figure out the largest number that goes into both 12 and 18. 6. Factors of 12 and 18. The biggest one that goes into both is 6. Number 2, 24 and 60. If you can't do this mentally, what do? Listen, why did we learn to make these trees? Because if the numbers get too big and you can't do it mentally, you make a tree. So for 12 and 18, for most of you, the numbers were smaller. You could figure it out. Now they made the numbers a little bigger, number 2, 24 and 60. There's still some of you in here that practice mental math enough that you could figure out the low 24 and 60. Some of you are still processing it. Many of you have figured it out. What's the largest number that goes into both 24 and 60? Here's a strategy you should use. Take the biggest factor of 24. 24. Does it go into 60? No. 2 days is 48 hours. 3 days is 72 hours. So 6. What's the next biggest factor of 24? Remember what we said? Whoa! It can only be half. Okay, wait! You can't get away. You can't get away. Your only homework, though, listen, is 1 through 8. 174. 174, 1 through 8.
Homework's just going down. We're only gonna get 1 through 7.
But I mean, at the same time,
It's in the Your Turn Now section.
I gotta thank you, but also for the homework on this work.